All right, so let's talk about a very special type of series called a geometric series. And a geometric series is the sum of a geometric sequence, and a geometric sequence is just a sequence in which every consecutive term is multiplied by a common ratio. So if you look back at the very first example we did, I'll scroll up here, where we have 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. That's a geometric series because we have a first term, 1/2, and then every term afterwards is multiplied by a half. So we have a common ratio of a half as well. So that's an example of a geometric series. And so we're going to take a look at these two. These are geometric series. And so first of all, we're just defining what a geometric series is. The key feature is that it has a common ratio. We have a first term and then a common ratio, and every subsequent term, every consecutive term is just multiplied by the common ratio, right? And then to get a series, then we're just adding up all those terms. Now, in example 3, we're asked to find an explicit formula for a finite geometric series. Now, a finite geometric series I just think of as being the partial sum. This is just a partial sum of the infinite geometric series, right? So this is a partial sum. And then, the actual series is this infinite geometric series. But we're going to start with the finite geometric series, the partial sum, and we're going to find a formula for the nth partial sum. All right, so what I'm going to do, I'm just going to write down what I have up above. So I have the nth partial sum is just equal to the first term plus the first term times r plus the first term times r squared, and so on, all the way down to the first term times r to the n minus 1. So that a r to the n minus 1 is the nth term, but you can see that the power of r is just lagging by 1. So now I'm going to do a sneaky trick to find this value Sn. I'm going to do something I think is awesome. I'm going to actually multiply this whole partial sum, this whole finite geometric sequence by r. Multiply everything by r. And so what I'll end up with is r times the sum that I'm looking for. But when I multiply this whole sum, I'm going to use the distributive property. And so when I take the first term, which is a, and multiply by r, I'm going to get ar. All right, now I'm writing it offset a little bit. You can see I'm kind of lining up these terms. These terms match. So, but I'm really just taking the first term times r. When I take the second term times r, I get ar squared. And the third term times r, I'll get ar cubed. And there will be an ar cubed somewhere in this dot, dot, dot. Now, there's also going to be somewhere in this dot, 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 an a times r to the n minus 2. And when I multiply that by r, I'm going to get ar to the n minus 1. And then finally, I'm going to multiply the last term times r. So I'm going to get ar to the n, right? I'm just adding the exponents. And so when I multiply the partial sum, this finite geometric series, times r, this is what I get. Now the sneaky thing is to subtract these two expressions here, these two equations. Right, I'm trying to find S sub n. So, but what happens when I subtract the two is I get Sn minus r Sn. I'm gonna still have this a value because I don't really have any term to match up for that. But you can see that all of these other terms match up, and so when you subtract, all these middle terms go away, and all we're left with is a. And then remember, we're subtracting the second equation, so we're getting a minus ar to the n. All right, so then I'm going to factor out Sn, right, because I'm going to solve for that. So I get Sn times 1 minus r is equal to, now I can also factor out an a. So I get a times 1 minus r to the n. And now I can just divide both sides by 1 minus r. All right, so what I end up with is s sub n is equal to a times 1 minus r to the n all over 1 minus r. Okay, so that's cool. So we got this nice explicit formula for the nth partial sum of this geometric series. Now I'm gonna go ahead and do example 4 at the same time here. And example 4 is just asking us to find an explicit formula for an infinite geometric series. So if we take what we have for the partial sum, we're just looking for the limit as n goes to infinity. So let's write that down. So we're trying to find the limit as n goes to infinity of this a times 1 minus r to the n all over 1 minus r. Okay, now the only place where n shows up is in this r to the n. So really nothing's going to change except this r to the n term. And so if our common ratio r, let me write that over here, if r is less than 1, okay, so or the absolute value of r is less than 1. So it's something like 1/2 or 1/3 or 5/8, or it could be negative too. We could have negative 1/2 or negative 3/8 or negative 11/16. As long as it's less than 1 and we're taking it to higher and higher and higher powers, that term is going to get smaller and smaller and smaller. All right, so that r to the n term goes to 0, and what we're left with is just basically 1 minus 0 times a, which is just a, all over 1 minus r. Now, I think that's awesome. We have a super simple little formula. So if we have an infinite geometric series, and we know the first term, and we know the common ratio, we can find the sum of that series, which is an infinite sum, right? It's the sum of an infinite number of numbers. But that is if the common ratio is less than 1. The absolute value of the common ratio is less than 1. So we're talking, I could rewrite this as r has to be between 1 and minus 1. Okay, so if that's true, then we have this nice formula for an infinite geometric series. If r is not greater than 1, or sorry, not less than 1, so it's greater than 1, right, or the absolute value is, then this term r to the n is just going to blow up, right? It's just going to go to infinity. So it's going to diverge. So if this thing is not true, right, that I have here, if that's not true, then it diverges. So otherwise, it diverges. Okay, so these are important results. So I've got a table here that I'm going to fill out just so you can keep this handy. So we have a nice handy formula for the sum of a finite geometric series, and it's just a times 1 minus r to the n all over 1 minus r. And if we have an infinite geometric series, the sum is a over 1 minus r if, right, so for r values that are less than 1. Absolute value of r is less than 1. All right, so basically r is between 1 and minus 1. So if that's true, then we have this nice little formula for an infinite geometric series. All right, so in the next example, we're going to apply this formula. So I'll see you in the next video.